TU Delft podcast.
We will divert from the book a bit. In fact, the content of the course was defined before we found the book that fits the best the contents of this course. But it's never 100%. So until now, well, the first 4 hours, first 2 blocks of the lectures were following the Anderson quite precisely, chapter 2 and 3. Last time you already saw it divert a bit. Today, most of it is covered by chapter 7, but we choose a different method. Main reason is that what we show here today is a simpler method to look at it than what they do in chapter 7. So if you try to study chapter 7 in advance and you thought it was quite complicated, you're right. We'll do it slightly simpler. Important topic, I said, for aircraft, for aeronautics, was also the opinion of Wilbur and Orville Wright. They said at some point during the development of their Wright Flyer, they already had the engines, they had knowledge of the airfoils, of the wings, how to generate lift. But the last problem they had to crack before they really could fly was the balance and control. And that's basically what they stated here when this one feature, balance and control, as they called it, has been worked out. The age of flying machines will have arrived. For all other difficulties are of minor importance. Why is it so hard? That's mainly because of the dynamic aspect, the fact that the time axis plays a role in it. So even if in a static case you can balance the forces, as you saw in the last lecture, then you still might have a very unstable aircraft, so you won't be able to enjoy that equilibrium for very long, because you will crash anyway. There's also the problem that Otto Lilienthal had. He had difficulty getting lateral stability, and this was basically how he crashed. Also, one of the Wright brothers broke his arm at one crash due to the lack of stability, also lateral stability. They were very scared by the death of Otto Lilienthal and really wanted themselves to avoid that fate, of course. So that was why they paid a lot of attention to this topic. Theodore von Karman talks about a spin, one of the most dangerous situations you can end up in, because it's very hard to get out of. You don't notice how you get into it, it's very hard to get out of. He compared it to a love affair. He was never married himself. I don't know if that means he had a lot of experience in this or less, I don't know. Also, it's still today, it's a hard topic. I mean, you would imagine, you see 2 aircraft here, you can hardly make out the left one, but you will very soon. Modern aircraft, and where even then, if you prove theoretically everything is right, with simulation and analysis, you go to the real test, it's still a hard problem. Let's see if these pictures work. It's always a surprise. Some day they do and some other days they don't. Here, YF-22 or 23 prototype. I hear sound, you don't. Tries to land, and at slow speed, everything becomes extra critical. Well, let's just... Oh, what does he mean here? Microphone line in, wrong jacket. Here, this one then. Cancel.
Crew malfunction sends Morgenfeld's aircraft into a violent oscillation.
You could see him going up and down very rapidly just before touchdown.
After skidding in flames for more than a mile, Morgenfeld walks away unharmed.
Pilot unharmed. That's not what you can say about the plane. You could see that at slow speed he suddenly started diverting, and that is basically what due to a pilot-induced oscillation, as they call it, PIO. Not that the pilot was doing like this to get the aircraft going like that, but he just responded automatically to the deviations that the aircraft had. So the aircraft was unstable, and he tried to correct, but then overcorrected and tried to correct again, and in this way, together they formed an unstable system, pilot and aircraft. Also, tilt rotors, very dangerous aircraft, and you can see that even there. Similar situation. And I think even here the crew survived. Of course, these accidents happened very close to the ground. So, not an easy topic, apparently, stability and control. Let's look at the pioneers, how they tackled this. For them, like Orville and Wilbur Wright said, it was a difficult problem to crack. You could see 2 different approaches in the old days between the European and the American pioneers. European pioneers tend to make their aircraft very stable, and therefore to get it around the corner, but not so agile that it would kill you immediately after takeoff. So you see that they moved around the canards and the directional controls, and also the ailerons. In this case, you cannot see the ailerons because the Wright Flyer used wing warping as aileron, which means that there is a line somewhere, hard to see. But if you pull on the stick, you would bring down the tip of the wing on the backside, and in this way you would control the aircraft. Oh, here you see it again. By just reducing the lift on one side and increasing on the other side, you can start a roll. What you basically control is the roll rate, so the rate of roll, not the roll angle. So it's very different from making a turn in a car, where you keep the steering wheel like this all the time during the turn. In an airplane, as the flight simulator gamers will know, I'll need one of them later. You pull to the left, you turn the aircraft a bit, you increase the lift force, and in that way, without extra lateral control, you pull yourself through the turn. And you roll back after the turn. Also the spin, we recently celebrated the spin centennial in Haarlem. The spin also had wing warping for roll control. Very dangerous airplane. The reason why we did not fly around the church one more time a century later was because we still thought it was too dangerous. Then it was Leon Lavasseur, the first one who came with a different type of ailerons, which basically just controls surfaces at the edge of the wing, controlling the aircraft like that. It was a real breakthrough then. This has been basically the model that we have been using ever since. Funny thing is that today we are discussing for new aircraft morphing wings with smart materials which you can electrically deform. We might return to the age of wing warping again because there are some aerodynamic benefits. So what other controls are there? Here are the standard ailerons. If you look at any airplane, most of the time the outward side is the aileron, the inboard side are the flaps. Sometimes all surfaces work together in more complex flight control systems. Other control surfaces, the elevator, which takes care of the pitch control. This is the roll control, pitch control. And the yaw control is done by the rudder, though they do not work fully independent. If you move the aircraft laterally, you in general will want to control both with the aileron and the rudder to avoid the aircraft from slipping through the air. If you just push the rudder with the pedals, that feels, very bad if you're in the aircraft. It's not very comfortable. In modern airliners, you often have the yaw damper in there, which will also control the rudder to avoid slipping maneuvers with the airliner. This is, by the way, a Spitfire which has clipped wings for low-level flying. And of course, the other control is the throttle. So in total, you have 4 degrees of freedom, you could say, in your controls. You have the elevator for pitch, the rudder for yaw, aileron for roll, and for forward acceleration to change the speed, you can use the throttle. Those are the 4 basic controls of the aircraft. And of course, the aircraft can move in 3 directions and has 3 angles around the 3 axes as well. So with 4 controls, you can manage to control an aircraft with 6 degrees of freedom, which is a funny thing if you think about it. I saw a question there. Slipping. Slipping is if you fly the aircraft with a relative to the airflow with the angle to the side, horizontally. So then you have more drag. It's often done by gliders, for instance, during the approach. If they want to brake, you often see them just pushing the rudder and the aircraft, sort of drifting with cars. You call it drifting, right? But it is indeed, you create a slip angle, and then you have airflow from the side, creating a lot of drag. Drifting itself, in aircraft refer to when the airplane moves different from its heading relative to the ground, so caused by the wind, for instance.
Is that something that happens during the crosswind landing?
Yes, during the crosswind landing, you want to slip on purpose because you want to align the nose with the direction of the runway for the wheels, while aerodynamically, if you have a crosswind, you need to steer up with a drift angle, basically, to make the aircraft go straight ahead. So then you need to slip, but to avoid going sideways, then you also need to roll to compensate that again. But then if you look at the airflow around an airplane, you slip. But this is way too complex. We're first going to look at a longitudinal static stability as an example. And the lateral cases are quite complex. You have side slips, drifts, indeed, controlled turns or slipping turns. That's a bit too much to deal mathematically today. Here we see the controls were for quite some time controlled by real wires in the aircraft. You can still see in many aircraft, small aircraft, you can see wires pulling the surfaces via levers, basically. Well, here are basically the connection, how you control them, how they are pulled. And this also has consequences for the sign conventions that we use. If you see here, for instance, a general aviation aircraft, the control wheel, if we move it to the side or if you move the stick to the side, you directly control the ailerons. With your pedals, you control the rudder. And with the pushing it to the front and back, you control the elevator, both for the stick or the control wheel. Well, the funny thing is, if you see here, you see the cables running from the side of the rudder to the pedal on the same side, which makes the rudder control for some people less intuitive. Because if you push your right feet, you will pull this cable, the rudder will move to the right, and you will go to the same side, to the right side. Well, if you compare it with a small cart that you build as a kid, if you move the front axis and you push the right side, you will go in that direction. With an aircraft, you will go in the other direction. So with the stick or the control wheel, it is as if the stick is connected to the airplane. So if you move the stick forward, the nose goes down, as if the airplane is connected to the stick underneath, like that. That's how the control, very intuitive. But with the yaw, you push on the right side and the airplane does not move in that direction, the airplane moves in the other direction. So that's a historic reason because of the cables. This was the easiest way to connect them. And for people, there were people who thought this was intuitive and people who thought the other thing was intuitive. But if you look at all the controls, it's not fully consistent. The rudder control is also the one that controls the nose wheel, by the way. So these are the controls, basic controls that we use. In modern aircraft, it's a bit more complex. You often have computers in between, which add stability if the aircraft is not stable, or take care of avoiding a slipping angle, and that kind of things. And also, in this case, you basically, in the end, you have cables controlling the surfaces, but you also have a computer connected to the same cables for the autopilot, who wants to control the same surfaces. And it gets more and more complex if you go to modern aircraft. In today's fly-by-wire aircraft, as they're called, the wire referring to not cables, but electrical wires, you basically have a computer in there who can give you a certain feeling that you control a very stable aircraft or very agile aircraft, while the real aircraft may have completely different handling qualities. And that what the computer then does is translate what you would like to do to what needs to be done to make the aircraft move in that direction. So here is a complete aircraft model inside the controller taking care of the right properties. It was first used in military jets because they wanted agility over stability. And if you make an unstable aircraft, you can make quicker turns, faster turns. But it was later also added to airliners for the purpose of weight saving. The electrical wires are much lighter than the cables that you need, the strong cables that you need for a large airliner. So there it pays off to you to get the extra complexity to save weight. Well, a little demo. I said I needed someone to fly this little model I have made on my laptop. but let's first see what we talk about. Because in the old days, like you saw with the pioneers and even today, people did not fully understand how stability worked. And what happened very often in those days, that they put test pilots in aircraft which were impossible to control. At certain speeds, sometimes certain altitudes, or sometimes even the complete flight regime. So one mechanism which caused many crashes with test pilots is the one I'd like to demonstrate with this little demo setup here. And I've made a little computer program, very simple one-dimensional simulation, in which you have a certain speed, and then you can calculate your next position or angle, if it's about an angular speed, but just taking the previous speed and adding the velocity times the time step. This is just basically the line that goes into the little program. And the same you can do with the acceleration to get the new speed. And these two are referred to as integrators, because if you go from position to speed, you differentiate by the time. And if you go from speed to acceleration, you differentiate again. But if you go in the other direction, we call it that you integrate. So these are called integrators, sometimes drawn as such. Having the acceleration going into an integrator gets the velocity. The velocity into an integrator gets the position. Well, what we now do is we show the effect of having integrators in your control loop. A very intuitive form of control is that we directly control the speed, for instance, and that we want to keep the aircraft at a certain place or angle. In that case, we basically control the rate, and this is very easy to do. You move up, the position changes up. You move down, the position goes down. You stop, it stays the same. So this is a loop with one integrator, which I've called mode 1. And you can just observe the position and feedback. Another way to do it, which I call mode 2, is have two integrators in there. Here you control the force or the acceleration on the aircraft. This is closer to real-life control of an aircraft. You control the change of the thing you want to control. Two integrators. Well, in the old days, they even made aircraft which had 3 integrators in there, which are called mode 3. Now I need some subject to demonstrate the effect. Is there somebody here who ever played a computer game? I think there are more. Is there somebody who has the guts to come in front of the audience here and try this little game? I see some hands. You in the back. If you could come down. It's not a very fancy game, it's just to demonstrate the effect. This is the control device. So, what's your name?
Laurens.
Laurens. Short applause for Laurens for having the guts to try it here in front of the audience. Okay, Laurens, I'll explain you what we're going to do. Let me see. So this is the little game. You're going to control a two-dimensional model of an F-16 with mode 1, 2, or 3. The idea is to keep it in the center, in basically the blue sky, and avoid the black zones above and below the blue zone. Just try it first in mode 1. If it works. It worked a few minutes ago. Let's just start it again to make sure it's completely reset. Okay. Okay. You still have to get used to it. Let's try again, mode 1 again. The controls are just like a real aircraft. So if you pull back, it goes up. If you move forward, you go down. You're right, that's quite essential information before you start. Let's see. Oh, it started already again. Okay, he's doing much better now, right? There is some turbulence. I forgot to tell, there's some turbulence. Well, you see a counter underneath, counting the amount of seconds that he's able to control the F-16 in this very turbulent weather and avoiding the black zones, which is basically, let's say, where the radar is or the AAA or something. I think you can keep this up indefinitely, right?
Oh. If I'm not gonna be disturbed.
Yeah. I think so. Okay, let's make it a bit harder, okay? Is that okay?
Welke controls komen er nu bij?
The controls are the same. We just add an integrator to the loop. But controls are the same. But it will react a bit more indirect now. Acceleration, mode 2. You feel it's different now, right?
Yeah. Harder, way more to. Oh.
Remember what I said about PIO?
What?
No, I'm talking to the audience. You just fly the plane. Well, not bad, not bad. So this is how most real aircraft fly, basically. They have a second order control 2 integrators in the loop. I think you can keep this up indefinitely as well. Time to make it a little harder, don't you think? Okay. Well, it's not a problem if you would not be able to do it in mode 3, but let's see how many seconds Laurens can control the aircraft with another integrator into the control loop. Okay?
Yeah.
Yes, ready?
Yeah, right.
3 integrators in the control loop. One more try? Yeah. You have to get used to it, right? Let's see, I think it auto starts. Yeah, it's very hard, this one. That's also indeed the point of the demonstration. So it's not a problem. Well, most people are unable to do this, so I mean, you're excused here. Very well done. Short applause, and you can go back to your seat. I'll put the game on the blackboard side, so you can challenge your housemates to see how well they will do. And Laurens set the standard here for, what was it, about 9 seconds or something? I've heard stories about that there are some people who are able to figure this out. After some practice, they can do automatically in their head the calculation for 3 integrators, because you control the chains of the chains of the chains, basically. And some people are able to do this. And I've heard records of like 30 seconds flight with this. The chain, how do they do this? Well, that's a bit complex to tell. It has to do with our aerodynamics. At some point, you automatically get the extra integrator due to the properties, the aerodynamic properties of the airplane. So this is what you normally get with a stable aircraft. You control the acceleration. You induce a force, basically, or a moment. But sometimes you get an extra integrator, especially in low speeds. In fact, there is a famous example of the... why doesn't this work anymore? So we didn't only crash the plane, we also crashed the computer. I know. This is a flying body of which NASA did a lot of research, and in fact many of those crashed due to the fact that they had an extra integrator in their loop due to the flying properties of this vehicle. In fact, maybe your parents will remember the $6 million man or something, the Man van 6 miljoen, as it was called in Dutch. This was a television series which, as their intro, ran a real footage of the crash of one of these aircraft in which the test pilot died. In the real story, he got a lot of bionic limbs and stuff, but in the television story, in the real story, the pilot died. So, very important to understand why something is stable. Therefore, we first need to look at some angles and axes, because we discussed forces at the aircraft the last time. Today, we're basically discussing the moments around the aircraft. This is the main axis that we define. The first axis we point in the direction of flight, or if it's the body axis, in the direction of the nose of the aircraft, and we call that X. The second is always pointed to the starboard, to the right side. We call it Y. And if we want a coordinate system that then has a right-hand rule for the third axis to make all our mathematics work, like cross products, we then automatically get a z-axis downward, which is not always the most convenient, because often we talk about altitudes, and we always have to add a minus sign there. But in terms of forces and moments, we use these three axes. Well, if we then talk about moments, I'll skip this for now. Well, first angles. No, this is... well, we discussed the controls. The elevator, the ailerons, and the rudder. They are all connected to one angle that you control. For the elevator, it's the pitch angle, and we use the symbol theta for that. Theta. Ailerons, there we use the phi, the phi, Greek phi. And for yaw, we use the psi. So here we get the angles, and they are automatically defined, the direction of those angles, by the direction of the axis. You point your thumb in the direction of the axis, and you automatically get, with your right-hand rule, you get the direction of the turn. For the control surfaces, we use the delta with an index indicating what kind of control we're talking about. R, aileron right, aileron left, or elevator. If you look at some of the angles a bit closer, for instance, the pitch angle, you basically see that it's built up of two other angles. And this is a very important picture to remember. So we have the pitch angle, which basically is the angle between the horizon and indicates the attitude of the aircraft, the pitch attitude. It's built up of two other angles. One is the angle of attack, which you discussed last time, where you saw that's basically the angle between the air speed, or in the other direction, the air flow, and the direction of the aircraft. And if you are not flying horizontally, you also have a climb angle. And your climb is, of course, determined by the direction of the speed. So this gives you this relation. The angle of attack plus the climb angle is the pitch angle. And we write it shorthand with alpha plus gamma is theta. So those are three different angles of which we need to know two to get the third one. For the moments, we use the same axis and we use different letters. So for the forces, we use X, Y, Z, or lift, drag, and what is the other one? Lift, drag, and side force, you always use Y. For the moments, we initially mainly looked at the pitch moment, and we called that M, moment M. And most of the initial discussions, also by pioneers, were about the pitch moment, the moment around the y-axis. Longitudinal moment, it's sometimes called. So how to get the aircraft stable, that it does not go up or down too fast, was the main priority. Making turns came later. So that's why we used the letter M for that moment. But then to make it consistent, we later added the L and the N for the other moments. So for X, Y, Z, we now have L, M, and N. In this lecture, we will focus mainly on this moment M. The L, of course, is the same letter that we use for the lift, so it can be very confusing. That's why we write it, if we talk about the L, we draw it very curly, similar trick as we did with the R. So L, M, and N. Pitching moment, M, nose up is positive, and that basically is what determines the direction of the y-axis. So if you want to have the moment positive if your nose is up, we use the right-hand rule again, point your fingers up, and you see your thumb move to the right side, and that's why we have let the y-axis move of point to the right. The origin of the axis, we normally use the center of gravity, because that's, of course, your reference if you talk about moments on a certain aircraft. So these are some conventions and notations we will use. Today we will focus on the moment, and we will focus from the angles, we will focus on the angle of attack mainly, and the result on the pitching moment. But the angle of attack we will focus on horizontal flight, so then the climb angle is 0, and a change in angle of attack is then equal to a change in pitch. So we make it a bit simpler. You saw all the angles now, but then we make it a bit simpler later on. This is what I discussed later, the lateral situation. Here you have the side slip angle, that's the angle between the heading and the actual course in the air. So here you have the airspeed, and here you have the direction of the nose. And normally there is no side slip angle. You want to avoid that because it generates a lot of drag. So normally there is no side slip angle, and then course and heading are the same. And in day-to-day speak, they are often confused. But heading is where you're looking, and course is where you're going. I shouldn't say heading to make confused, but the course is where you're going. We use the angle between north to be right. We should have drawn this the other way around because we use it. If you look at the top view, it goes like in that direction. Well, last time we saw coefficients used for the lift and the drag, and we're going to do the same for the moments. But let's look at the coefficients a bit further. Herefore, I'll need a tablet to make it not too fast. So last time, you got this relation. L is lift coefficient times half rho squared half rho v squared times the wing area. It's for the lift. There are different ways to look at this equation. One is the physical way, the physics way. If you look at it, you can say this gives the relation between different quantities, the air density, the effect of air density on the lift force, the effect of speed, airspeed on the lift force, the effect of wing surface on the lift force. And this is physically true. This is a true physical relation. But we often also talk about this as that this is the force with a dimension, with a unit being in newtons. And this is also the force, but then without its dimension. So we sometimes call it not just lift coefficient, but actually the dimensionless lift force. And it has a reason, because often these things change. You change your altitude, you change your airspeed, and if you're designing an aircraft, you do not yet know what amount of wing you're going to need. And you still want to see what's happening or what will be causing the different forces. So if you want to talk about all altitudes and all airspeeds, and even perhaps different wing areas, you better talk about the lift coefficient, the dimensionless lift force. Because if you find something that's true for the dimensionless force, it will be true for all densities and all airspeeds. So all altitudes and all speeds. In other words, your complete flight envelope. So what does this mean? What does the CL stand for? If we here have the atmospheric situation here, the air density in there, here we have the airspeed, there the area of the wing, surface of the wing. What are the variables that are captured by the lift coefficient? What were those? What makes, in other words, what makes the lift coefficient change? The airfoil, that's right. So that the shape of the wing, of the shape of the airfoil, generates a different lift coefficient, because that's not captured by the others. The other thing? Angle of attack, right. The angle of attack is also will change the lift coefficient. So the angle is not in this relation somewhere else. It has a huge effect on the lift, obviously. So that is indeed changing the lift coefficient. So this basically captures the shape of the flow, and that's determined by the shape of the airfoil, the angle of attack, and if you look a bit closer, also a bit the speed regime that you're in. There are some effects with higher speeds which will make this not completely true anymore. So v squared works for subsonic speeds, but if you go supersonic, or if you change scales, so if we talk about an insect versus a Boeing 747, the scale effect will also have an influence. In general, we could say CL captures the shape of the flow. Also, there's a functional reason to write it as such, and that is, it's very handy to talk about the dimensionless force instead of the true lift force. Imagine that I'm an aircraft designer, and I want to select an airfoil. Then I could ask my aerodynamics guys, well, what kind of airfoil do I need? Give me a good one. I just want a good airfoil, right? We all need the same airfoil, the best. And then they will ask, well, how high do you want to fly? Well, I say, depends. I want to fly at sea level, but preferably I would also like to get a bit higher. So what speeds do you want to fly? Well, yeah, of course you want a takeoff speed, landing speed, but also faster to get to our destination a bit faster than with our takeoff and landing speed. Well, then he will say, well, then I cannot help you, because if I do a wind tunnel measurement, I need the atmospheric density, and I need the speed, and I need the wing area. What's your wing area? I say, well, I don't know. It depends on the airfoil. So you will see this isn't really working very well like that, right? We're not getting anywhere there. So therefore, it's good to separate the problem and to say, okay, then, you know, I can tell the aerodynamics guy, forget about the density and the airspeed. I'll sort it out myself. Just give me the CL and CD of an airfoil and CM, the moment coefficient, of an airfoil, and then show me how it changes with the angle of attack and for a certain scale which I have in mind. And then I can get relations, like you saw last time, CL alpha graphs, which will look something like this. We have the angle of attack on the horizontal axis, we have the CL on the vertical axis, and we will get something like this. So what do we see here? We see that if the angle of attack increases, we get a lift coefficient which also increases, but there's a certain limit to which you can go, and then the aircraft will stall, and the sort of flow will become chaotic and not generate a lot of lift anymore. It might even go to zero or below zero. If you have a good airfoil, you can also see that even if the angle of attack is zero, we still get some lift. And sometimes we talk about the absolute angle of attack, because then we just move the y-axis to the point where the CL crosses zero, and that makes it slightly easier to discuss CL alpha, a simpler relation. So CL alpha, CL is basically our lift force, and we can also see this as our lift force for this angle of attack, when ignoring what speed or altitude we're actually flying at. This will help me, if I compare this with CD or with the CM, to select a certain airfoil for my wing, but also for my elevator. Because this relation doesn't only go for the complete aircraft, but it also goes for the wing or parts of the aircraft like the horizontal surface. Lift is the CL times half rho v squared times S. The half rho v squared is called the dynamic pressure. Did Mr. Sinke mention this? Dynamic pressure last time? Dynamic pressure Q is half rho v squared. This should look familiar to some of you in high school. Got the law of Bernoulli, and what Bernoulli basically says that the pressure, the total pressure, is the static pressure plus the dynamic pressure, which is constant. In other words, the P that you measure plus half rho v squared is constant along a streamline, along the flow, in the direction of the flow. So this is this is not just a general P, this is the static P, and this is the dynamic pressure. So if you look at this relation, you can see that if the speed is 0, then all we feel as a pressure is the static pressure. And if along a stream like this is constant, this also means that if you would put your hand outside a car window or plane window and you would stop the flow, then you basically at your hand make the speed 0, then you will feel the total pressure. And on the other side of your hand will be the static pressure of the atmosphere. So basically the net force that you feel at your hand is the dynamic pressure. So to get a feeling what the dynamic pressure really is, it's basically the force, the pressure that you feel if you stick your hand in the flow and you stop the flow completely. So that's called the dynamic pressure. It's a clear indicator for the airspeed. It increases quadratically with the speed and is also a factor which scales all the aerodynamic forces and moments at an aircraft. So if v squared becomes twice as high, all the forces will be twice as high. And rho, of course, are directly the amount of mass that you feel, so there it scales linearly. So this is very important to keep in mind, the dynamic pressure. It's also used often to capture everything in one, but the pressure is not really easy to imagine. So putting a number to this doesn't often really give you a good feeling. So what we often do is that we say, if we have a certain dynamic pressure with the true airspeed filled into the equation, I can also say, well, this would be equivalent to flying this amount of, for instance, flying 200 knots at 10,000 feet, feels, because of the thinner air, equivalent to 150, for instance, at sea level. So if we use a constant density, the atmospheric density at sea level, and we equate this to the real dynamic pressure, we can calculate the equivalent airspeed. And then there's something we can really imagine. So an aircraft flies always the same with the same equivalent airspeed, because that indicates the amount of dynamic pressure that the airplane feels. So this also means if you go higher in thinner air, you have to fly faster to get the same flow, which makes sense. We could also write this the other way around. We could say equivalent airspeed is rho divided by rho 0 times t and the square root of that, the true airspeed. So TAS is true airspeed, the real airspeed, and equivalent airspeed, EAS, is the one that basically for the flow is much more important. It doesn't really matter that your real airspeed is 200 knots. If the aircraft has a stalling speed of 150 knots, it will stall anyway, because those stall speed was calibrated at sea level. So all your red zones on the speed indicator are calibrated at sea level, and this is why the instruments inside an airplane also indicate the indicated airspeed, which is very close to the equivalent airspeed. There's only some instrument effects between them, but we'll leave that out for them. So in our lectures, we will say the indicated airspeed in a plane, even in modern planes, is the same as the equivalent airspeed. It's not completely true. There are some effects of how we measure airspeed in between, which will be dealt with later. But for module A, B, and I think for all of the course, we say IAS is EAS. Indicated airspeed is equivalent airspeed. But it's important to keep in mind that this stands for the dynamic pressure. And this means that if you have, for instance, a CL that is 1, CL that is 1, that is a normal value. Often the CL maximum is even above 1. So if we have a CL that's 1, 1.0 here at some point, then imagine what that means. That means that the lift force that we get is basically equal to this, which basically means that it would be the same if we would use the complete wing surface, which is now put horizontally, if we put that vertically and stop the flow with that wing surface, stop the flow completely, then that force that you would then get is the same as you get with the lift force when the CL is 1, which is a sort of figure close to a CL max. It's often 1.4, 1.6, those kind of values for CL. But imagine what an enormous force, lift force, we can trigger if you have a CL of 1. The same as the complete force if you would just put the wing out in the flow and stop the flow completely. The flow that you feel if the wing was perpendicular, the force that you would feel if the wing was perpendicular to the flow. So that's the real meaning of CL, and we need to know that we can just regard this as the lift force, but then without dimensions, because if you calculate the dimensions of all of this, you already get newtons. So it has no units, which is not very strange, because it captures a shape, and that doesn't have any units. So if you put in kilograms per cubic meter, meter per second squared, and squared meters here, you would get kilogram times meter per second squared, which is the same as Newton. So if we talk about the dimensionless lift force, we talk about the CL. And that's what we will use in the second hour to calculate in our stability calculation. So let's take a little break now. If you haven't got the handout yet, a few of the questions I got during the break showed that I did not explain something very clearly to some of you. So, once more, it is not true that the lift coefficient is 1 if you have the wing perpendicular to the flow. Okay, it will be very, very much less. What I tried to say is that normally this is around like 10 degrees or something. So if you have an angle of attack of around 10 degrees, you will have a lift coefficient in the order of 1. Of course, this depends on the airfoil, but this is around, gives you sort of the order of magnitude. So it's very minimal angle of attack. Well, 10 degrees is still a lot for aerodynamics. But just to give an idea of the magnitude of the force, it would be the same as if you would stop the flow, so you would need a shape more like this, I guess. The force that you would feel as a drag if you use a sort of container that has a similar surface in the back as the surface of the wing. So that's what I meant when I said if you put the wing perpendicular in the flow, then the horizontal force you would feel has the same order of magnitude as the lift force that you feel when you have a CL of 1. Just to indicate the intense force, the huge force that you feel when you only have a fraction, like 5% or something like that, of the drag. Remember CD over CL ratios that were discussed in the last time. So something like 0.05 is then the drag coefficient when you have a CL of 1. Okay. Now if we then look at CLs and all these coefficients in a different way as dimensionless forces, you basically would say this is our dimensionless lift force, and is defined as the real lift force divided by half rho v squared times s. Same for the lift force of the horizontal surface. We'll use the notation h added to that. And this is the lift force of the horizontal surface and divided by half rho v squared, but then also the surface of the horizontal surface, the area of the horizontal surface. This because when the aerodynamics measured this airfoil, they of course didn't know whether you were going to use it for a horizontal surface or for a wing or for a rudder. So they gave it for a wing which had that airfoil with that area. Also would like dimensionless unit, because then it's true for all altitudes and all speeds. So there we also use the same trick, but of course a moment is in Newton meters. It turns out that this scales up with the average chord of the wing. So if you make the chord twice as large, so in that direction you enlarge the wing, then all the arms of the aerodynamic forces will also be twice as much, so that's also scales up. So if we add that dimensionless, we again have a unit without units, without the dimension, which is dimensionless pitching moment. So these three definitions will be used to look at the stability of an airplane. Because what the Wright brothers were trying to do was to figure out how can we make sure that when we fly, that the airplane will not go up very fast or go down very fast if there's a small deviation. So that's what we will use for that. But first we have to see, I'll skip this for now, what stability is. What is stability? When something is stable, what does it mean?
Equilibrium.
There's an equilibrium, but there are also unstable equilibriums. So sometimes you have something that's in equilibrium. For instance, if you take a pencil and you put it on its tip, if it's exactly vertical, there's an equilibrium. But it's an unstable equilibrium, and in general it will not last very long. Yes, that is indeed a definition which we can translate to mathematical properties. So if there is a change out of the equilibrium, so there is an equilibrium. If, for instance, this is a stable situation, if we move the ball a bit up, then the reaction will be in the other direction, opposite direction. So, and the same if we do it in that direction. So therefore, if there's a small change, and there's always some noise, there's always some change, if there's a small change, it will go back and then it stays here. Well, if we put a ball here, a sphere here, on this curved surface, you can see that if it's exactly in the middle, there's equilibrium, but the tiniest of movements will make it go to one side, because then it will go even better. So it will amplify deviations, and here it will counter deviations. But look at those two arrows. Opposite direction, stable, and here, if we would draw the arrow of the force, it would be in the same direction. If we formulate it mathematically, if we multiply those two, or divide them, then we get a minus when it's stable, and a plus sign when it's unstable, because it could be minus minus, you multiply or divide it, it's positive, or plus plus, you multiply or divide it, it's positive. So if we multiply or divide the force by the deviation, and we get a minus sign, then we will have a stable situation. Here are other examples looking at the shape. I think the lowest one indicates it the clearest. If we talk about this equilibrium situation and whether it wants to return to that, that is what we call the static stability. So the stability which we can figure out by just looking at a non-moving picture. We can figure out here what would happen if it changes. There's also a dynamic stability, and that is that even though the initial move here, this is a dynamically unstable situation, even when the initial reaction is right, so it moves back to the zero deviation, it could be such that it picks up so much speed that it diverges further next time, and we get this oscillation. And this is dynamically unstable. This is dynamically indifferent, neutral, and this is dynamically stable. So you can see that already looking in one axis, this is quite complex to figure this out mathematically. We have to see when this is damped and when this is undamped, and this also depends on the frequency of the movements. It gets very complex. So for today, let's focus on static stability, because that has to be true anyway. And we leave this for later. I think third year is when you will get this mathematically. You need to know what it is today. So let's look at the longitudinal static stability. Longitudinal means in the pitch direction, and if we talk about lateral, it has to do with sideways movements or rolling. Like I said, we also leave that out of the discussion today. So today we talk about the longitudinal static stability, and that's the title of the handout. So therefore we use the three definitions that we just saw, and if you would just read along with me the handout while I do the derivation, and you could add your notes to the handout, that will save you some writing. Because this is again one of those derivations that you have to know on the exam. And the reason is that this only, the one that we will derive today, is only true for conventional aircraft, and your job as a designer later will be to change the shape. To, for instance, leave out the horizontal tail, or use a canard airplane, or what was the picture outside of the Piaggio, slim, sleek, sexy or something. They have both a canard and a horizontal surface in the back. Is that a good idea? You will be able to calculate those things, you need to calculate those things when you design an aircraft. Today I will derive it for standard configuration as an example, and you can figure out that you might have to do it for a canard or a flying wing or who knows what, but for another configuration at the exam. So it is about shapes of the airplane configurations that we use. There are many different configurations, and you see them here. Aft tail, that's the standard one. Tail first or canard. Free surfaces, that's the Piaggio layout. Tandem wing, tail less, 2-1, flying wing and a delta wing. How do you decide upon those configurations and, more importantly, the size of the tail? When is an aircraft stable? You need to know before you put a test pilot in, preferably. So, what we saw about the definition of stable, we can translate this to a flying aircraft. If we talk about the pitch, it means that if the aircraft pitches up due to a bit of turbulence or somebody moving the stick a little, if the aircraft goes up and the alpha increases, because that will generate the moment, the angle of attack. If the alpha increases, if delta alpha is positive, then remember that the y-axis is pointed away from us in this picture, and the standard convention for moments, for plus moments, is in this direction in this picture. So nose up. Nose up is positive. So what do we want as a reaction to a positive change of the angle of attack? What kind of moment do we want? Positive or negative? Negative. Yes, has to counter the direction. So if delta alpha is larger than 0, then we want a delta, a change of the pitching moment, smaller than 0. And the other way around, if the change of angle of attack is smaller than 0, plane moves down. What kind of moment do we want then? Positive or negative? Positive, larger than 0. In other words, we could say that the change of the pitching moment divided by the change of the angle of attack has to be smaller than 0 for a stable aircraft. So if delta Cm divided by delta alpha is smaller than 0, then we have a stable aircraft. This should also go for very small changes. So with small changes we write d instead of delta. dCm d alpha should be smaller than 0. And this we can also read, of course, as the derivative of the pitching moment by alpha. And this indicates how we need to calculate that then, mathematically. So apparently we have to look at the dCm d alpha. This is often written also as Cm derived by alpha. So similarly, you could say if we look at the angle of the CL alpha curve, and we look at the steepness of it, we call that dCl d alpha, and that we also write as CL alpha. So this is a form of notation. If you see a second index, this often refers to either a 0, being the neutral, or a place, but if it's an alpha, it means the change of this coefficient due to a change in alpha, because that's where the derivative stands for, right? Delta y delta x was the change of the y per x. So this is the change of the pitching moment per alpha. Or if you say it correctly, it's the change of the dimensionless pitching moment per degree alpha. So a stable aircraft, we know, has to satisfy this relation. And of course it also has to be trimmed. If you want to see what it means that it's trimmed, we have to say, basically, here we say that it has to go down. The cm of the aircraft has to go down when alpha increases. This is basically graphically the same thing. If cm alpha is negative, this means the curve, the line, it's a straight, nearly straight line, has to go down. But also, there has to be a point where it's 0, because that's the equilibrium. In other words, we call this the trim point. Well, we can move this curve up and down by changing the trim angle, or basically the change of angle of attack, between the horizontal surface and the wing surface. So, but to have a stable equilibrium, we first need an equilibrium, so there needs to be a trim point, and we need a line going down. You could also say that when the lift is 0, I mean this goes up with the lift, right? The CL will also go up in that direction. Our lift is probably larger than 0. So if we make sure that when our lift is 0 and the CM is then positive, then we will certainly have a trim point. So a very simple relation that we also say often for stability are 2 criteria. There needs to be a trim point. Cm when Cl is 0 is larger than 0, and the Cm alpha is smaller than 0. If you have those 2 criteria satisfied, we will have longitudinal static stability. We will not crash, because that's what we're trying to avoid here. Well, let's look at the trim angle and the horizontal surface a bit closer, because that is key to providing longitudinal static stability. It's all about the horizontal tail surface. The size of the horizontal tail surface is mainly determined by making the aircraft longitudinal statically stable. So if we have a wing which has a certain angle of attack because the air flows up in this direction, this is often also what we call the angle of attack of the plane. Let's look at the wing and the fuselage as one. So we divide the airplane in 2 parts, wing and body, and the horizontal tail. But I'll draw only the wing. What happens, how do we generate lift? Well, we generate lift by moving the air downwards a little. So the air is moved a little bit downward. I take it exaggerated with these arrows here. Which means that at the tail, the angle of attack will be slightly less, because this is the angle of attack, and this is basically the epsilon, the downwash generated by the wing. So this is the flow, this is the same, but this is the real flow, and this one is actually epsilon, and this together is the original alpha that we had at the wing. Well, that's not a good thing if we need more lift. So, and if we need to trim the aircraft, we can change the horizontal surface. So what we normally do is we trim it, for instance, we trim it up a bit, so it's different then from the angle of attack from the wing, with its angle, alpha. So we add a little trimming angle, which we call IH, incidence of the horizontal, angle of incidence of the horizontal surface. And then we have the angle of attack, alpha, H. We have it now increased, and because we have lost a part of the epsilon part compared to the original alpha. So from this figure, you can see, this should be the angle of attack of H. It's a bit difficult to write all the small indices on here. From this, we can see that if you want to calculate the angle of attack at the horizontal surface, you take the original angle of attack, we subtract the downwash, and we add the trim setting of the horizontal surface. So now we know the angle of attack at the horizontal surface. And that's something we need, because we are going to look at those two surfaces later on. It also means that if we change the angle of attack, that the angle of attack at the horizontal surface, if we have a small deviation from our stable situation, that it will have a different effect on our horizontal surface. And we can see the change of angle of attack at the horizontal surface per change of alpha. So if alpha changes, what happens then to the horizontal surface angle of attack? Just by differentiating this equation to alpha. Well, alpha becomes 1. Epsilon, well, we do not know the exact properties, but let's call it the epsilon, the alpha. What happens with the angle of incidence? Well, if there's a small deviation, we assume that the pilot doesn't start turning the trim wheel immediately. Right? We're looking at the airplane hands-off. It has to be stable without control of the pilot. So it won't change. The DIH, the alpha, is 0. So which means that we can keep this relation if we want to know the change at the angle of attack, of the horizontal surface per change of angle of attack of the whole aircraft. Clear? No. What is not clear? Why we need it, I will show you later, but is the relation clear? What it means? Is that clear? Sorry, first in the back, then I can. What exactly is the downwash? The downwash is the effect of having a wing in front of you. A wing generates lift, and it does so by pushing air downwards, which means that the direction at which the air is coming at you has already decreased a little because of the wing. And the difference between those two angles of attack is what we call the downwash, epsilon. And you can imagine that if you have a different angle of attack, you will get more lift, so you get more downwash. So this number is generally positive. And of course, if the tail is very, very far away from the wing, you will have less downwash because the flow will have recovered a bit already.
Why do you say that the IH
That is because the IH is nothing else than the angle that the pilot has set the horizontal surface to with his trimming wheel to get an equilibrium without having to pull the control column all the time. So the pilot is flying, he notices that he has to pull all the time to keep the aircraft straight, then he will turn the trimming wheel, so the force will go away, and what it does basically is it sets the complete horizontal surface in a little angle up or down. And it doesn't move when the small deviation of angle of attack, for instance turbulence or something, causes something, it doesn't move because the pilot is not turning the trimming wheel immediately. At least we assume that he is hands-off. There was a question there? Answered already. So this is very important to understand what we do when we differentiate, when we calculate the derivative of alpha h by alpha. It's always this notation from d alpha h, or dcm, d alpha. It's not just one property derived to the other, differentiated, but it's also the change of this value per change of the other. So this is just something we have to do before, without knowing why yet, but that's something we will encounter when we will try to figure out how do we make the Cm alpha negative. And therefore we use the picture, it's also in your handout on page 5. We have to look at the complete configuration, so we take the horizontal tail, we have a lift of the wing, L, we have a lift of the horizontal tail, LH, and we have the weight in the center of gravity. Let's draw it in the middle between the two wings. And then we know that there's always a moment when you generate lift with a wing. One of the problems of a flying wing is that when you increase the angle of attack, the moment changes, and you basically need to counter it with, for instance, a horizontal tail surface. So this is what we call the moment, and we take it around a point that we call the aerodynamic center. And that is because then we will get a moment around the aerodynamic center, and we just have chosen this point. We can choose any point, but we've just chosen this point for one specific property. And that is that at that point, if the angle of attack changes, the lift force changes, so the force in that point changes, but the moment doesn't. You can find out because it's a linear relation. If you just move this point, first it will descend, then it will go up, and at some point it remains the same. That's what we call the aerodynamic center. So that's useful because, as you can already feel coming, to get stability, we later are going to change the angle of attack a little and see what happens. And this doesn't change then, and that's very convenient because then the derivative is 0 and it will disappear. So all of this is aimed at seeing what happens when we change the angle of attack, and that's to choose a convenient point. We choose the aerodynamic center. An important definition, aerodynamic center is the point where the aerodynamic moment does not change as a result of change of angle of attack. In other words, dmac, d alpha is 0. Well, if there's an equilibrium in forces, we can also see here, this I should add the W here, this is the weight. Well, to keep flying we have to have an equilibrium in forces, and we assume here we have this equilibrium because we want to look at the change at the equilibrium. So this means the weight is equal to the lift force of the wing and the lift force of the horizontal tail. The wing body, let's call this one the wing body, and we call this the total lift of the aircraft. So there's the equilibrium, so the weight is equal to the total lift, and the total lift consists of those two forces. Okay, now we have to see what the moment is. Well, to have a moment, we have to look at the arms of the different forces. Well, we use the aerodynamic center of the wing as a sort of reference. And the difference between the center of gravity and the aerodynamic center we call LCG, and the difference between the place where the horizontal surface acts we call LH. There is no moment drawn at the horizontal surface. Does anybody know why? The moment of an airfoil happens when there is a camber in the airfoil. Remember last time when we discussed airfoils that there is a certain camber? That causes the moment. When we have a symmetrical airfoil, there is no moment. We can choose a point where the moment is 0 and it will remain 0. So at the aerodynamic center of a symmetrical airfoil, there it will remain 0. So we can leave out the MH there. The only moment we get from the horizontal tail is the lift force times the arm. So let's write the total moment first. Total moment around the center of gravity. Well, that is the moment around the aerodynamic center. You can move moments around, so it doesn't really matter where it is. If there's equilibrium, the moment has to be 0 with regards to any point. So you can just move moments around and they won't change. You can see them as two forces with a little arm in between. Clockwise positive, yes, nose up. So we're looking at M plus, as you can see in the handout as well. M is plus nose up. So then we have to see what the lift is of the wing. It is also positive. Wing body times LCG, that's the arm. And we see that the lift of the tail is negative, and we cannot use LH there, but we use LH minus LCG. So this is the total moment around the center of gravity of all the aerodynamic forces. Is this all clear? So now we want to know, well, we can first simplify this a bit further. Let's try to simplify it one step further. If we take away the brackets, we see that we get LCG times LH plus LH times LCG. LH times LH, LCG times LWB, like this. Taking the brackets away, and here we see that this plus this was equal to L. In other words, for the complete aircraft we can say it's L times LG minus LH times LH. This is basically also the equation we would have gotten if we would have used the aerodynamic center as a point of reference, which again shows us it doesn't really matter which point you take. Now we have to look at the change of this as a result of the change of angle of attack. So let's first make this dimensionless. That's the best way to get rid of a lot of variables, because the speed and the density, everything is in here. So if we make it dimensionless, we get m divided by half rho v squared SC, and we have to divide everything by this. So plus L times LCG, half rho v squared SC, minus LH times LH, that's half rho v squared SC. Here we can see that a lot of things are the same, so we can rewrite this. This is basically the CM, because that's where we're getting it. This basically is the CL. Without the C here, we get the CL. And here, that doesn't really work that well, because this is the area of the wing, and if we use the CL of the airfoil, we do get the we should use the surface, the airfoil. So there, we can, if we want to replace this by CLH, we still have to multiply it by SH and divide it by S. In other words, if we write this as a dimensionless equation, you can see it in the handout as well, we get Cm is Cm in the aerodynamic center plus Cl times LCG divided by the average chord minus CLH times LH divided by the chord, but also the two different surfaces. So CLH times LH divided by S is basically what we had at the previous slide, times LH over C. This together, we have given a convenient name. We call this the tail volume. So this is basically the ratio between the arm of the horizontal surface and the chord of the wing and the two areas. This is just for notation. It doesn't have a physical meaning. It's not a real volume. So we can write the same equation dimensionless again. Cm aerodynamic chord plus Cl times LCG C minus CLH times VH. So remember, there's still it's in dimensionless shape. It's written, but still it still says the same. The total moment around the aircraft is the moment around the aerodynamic center. The lift force times this arm, also made dimensionless, times the lift force of the horizontal tail times the tail volume. Nothing else than the moment equation, but then written in coefficients. Now we should derive this to alpha. So dCm d alpha. Well, we know that the moment in the aerodynamic center doesn't change when we change alpha. So here we can write 0 immediately. Also, the distance between the center of gravity and the wing will not change when we change the angle of attack. But the lift will. Let's just write that derivative there, CL alpha times LCG C minus CLH alpha times VH. VH also won't change because those are just shape parameters. So this is the DCM d alpha, or CM alpha as we normally write them, written out using the lift coefficients for the complete airplane. So now, this is something the aerodynamic guys will give us. The change in CL for alpha. This is just the steepness of the C alpha curve in the graph. It's often written for a certain airfoil, they will call this A. I warned you that we would reuse the letter A a lot of times. So this is often called A times LCG over C. But for the horizontal tail, we do not have the change of lift of horizontal tail as a result of change of angle of attack of the complete aircraft. Because that's something they didn't measure when they measured the airfoils, because they didn't know how we would use it in the airplane. But there we do the same trick as we did in the atmosphere calculations with temperature and altitude. We say, okay, what do we know? We know the change in CLH due to the local angle of attack. That is just something that you get when you take the airfoil from the book, you ask the aerodynamics guys, and they will give you this. If we then multiply this by the change of the local angle of attack as a result of the total angle of attack, there you can see that this is basically, all of this is the same as the one that we're looking for here. Now you see why we calculated this in advance. Because this, apparently, we can just get out of the book, a property of the airfoil, and this we have calculated on the 2 slides ago. So this we get out of the book. It's called A for the tail, for instance, we call it, I think. What letter did I use in the handout? T or H, or both are used. T, I think, for tail. Okay, fine. So this is something we get out of the book, AT, from, it is a property of the airfoil. And this we have calculated on the previous slide. So what basically we have here is AT times VH. But now we have to correct for D alpha H D alpha. So this is the AT and this is the alpha H D alpha. Well, we calculated that one. So basically it's A times LCG divided by the average scored. Minus AT VH times 1 minus the epsilon the alpha. The epsilon the alpha is normally given if you get a certain wing for an aircraft and you know the distance where you're going to put the horizontal surface. They will tell you, well, you lose about 10%, for instance. So typical values of the epsilon the alpha are, for instance, in the order of 0.1. So this is the CM alpha. So what kind of CM alpha did we need to have a stable aircraft? Because that's why we started this whole derivation with all the CM alpha and stuff. We wanted a statically stable aircraft. And that we translated to a certain property for the CM alpha. It had to be smaller than 0, negative, exactly. So let's look at the border case here, or if it has to be smaller than 0, we need this to be large or this to be small. Right? If we want CM alpha smaller than 0. And the first part is also the part that generates the lift for our aircraft. Look, it's the change of lift as a result of angle of attack. So the performance guys will say, no, I want this to be big, not to be small. And then the stability guy goes, no, you should keep it really small, make a huge tail, it will be much stabler. Yes, sure, but we also want performance. So that's again balancing two properties. In other words, if we look at the borderline case, we say CM alpha. So it's just neutral points, you could say. If we look at neutral stability, we could say CM alpha is 0. We get basically that this relation, so 0 is A times LCG over the chord minus ATVH1 d epsilon d alpha. In other words, we could also say that the center of gravity has to be within a certain range to keep the aircraft stable once it is designed. So imagine we already know what the aircraft looks like, then we still can play with the location of center of gravity. So in this case, when it's 0, if we put it to the other side, let's move this to that direction and then revert it. Say ALCG over C is equal to ATVH1 minus the epsilon the alpha. So then it's on the edge of stability. It's neutral stability. In other words, the LCG over C has to be ET divided by EH, my 1 the epsilon the alpha. This point is called the neutral point. And it had to be, it's in this vector that had to be small, remember? So we say that if the LCG is smaller, LNP is smaller than the LNP, then we have a stable aircraft. And in normal language, this means a front center of gravity, moving the center of gravity more to the front makes a more stable aircraft. It doesn't have to be before the wing. It can be in between the horizontal surface and the wing, as long as it is not too far back to cause instability. We are nearly running out of time, but as a last demo, you got this paper full of very complex formula. You know, all the matrices, stick, free, static, longitudinal stability. This is how we explain it to third-year students. So you got this because you need to fold an airplane of it right now. And then I will demonstrate the effect of the center of gravity. So try to make a paper airplane out of this once you've finished writing. To the best of your knowledge, a stable aircraft, and I need 2 volunteers here. Can I, yeah, it's on the corner, it's always a risky position. Can you two please come to the front? Without the airplane. Fold the airplane, don't throw them yet, because I want to explain something using that. Okay? En dan liggen daar paperclips aan de plakband. Dan maak je 2 of 3 paperclips aan de voorkant vast om het zwaartepunt naar voren te schuiven. En dan zal je zien dat ze daarna stabiel zijn. Oké? So don't study those formula, right? There was one guy who left after the first hour. I warned him, if there are more, it's your responsibility to avoid them studying this for the exam. But, so, if you have folded your airplane, I have 2 plane catchers here in the front, and they will pick out an unstable aircraft. Each of them. And then we will change the center of gravity to make it stable. But of course, if you all did your work correctly, they won't have any work. So I also make an airplane, which probably is unstable. Okay. So are you all done? Beautiful designs. So I'll count to 3, and then you all throw them, and you will catch 2 unstable aircraft. Okay? Throw at them a bit, or a bit here. And I said 1, 2, 3, go. Look, there's a good one, an unstable one. With the yellow shirt, please throw. throw them. Yeah, throw it here to the front. Right. Oh, that's a very... You want that one. And that's also an unstable one. Here. No, another one. I think the longer one. Okay. Please, all of you also take one with you, okay, afterwards. Let me see, is this an unstable one? Longitudinal. You both have an unstable one? Yeah. Way too good, most of them, right? Okay, just add. This one is also unstable. Okay, now we're going to add 2 paper clips to the front. And then the center of gravity will have moved to the nose. And then it should be stable. That's an unstable one. So if you ever, after this education, decide to be, for instance, a business consultant or work at a bank, then at least you can still use your knowledge, because you will probably have paper and paper clips at hand. And those jobs are, in my opinion, very boring, so you better then try to do something useful. Like trimming an aircraft. Let's see if you're able to make them stable. That one is now stable because it came flying down like this, and now it flies in a straight line. The lift could be better, but it's still stable. The unstable ones you can recognize by the one that make a flight like this, really going up and down, getting worse and worse until they actually stall. And then adding a paperclip, otherwise try it at home, should make it stable. Okay, there is some homework. Thank you very much. There is some homework as well, other than folding airplanes. Please try problems 7.1 till 7.6 and then 7.9. Then you will go through the same steps as we did today, but then with numbers, and try to see how this works. Please, all of you, take at least one of those paper airplanes and put them in the container outside. That will serve safety concierges a lot of work. Thank you very much.
Please visit our OpenCourseware website for more information. See you at our next